All right, everybody. Welcome to lesson 1.2 for Honors Pre-Calculus. This lesson is called Functions. And what we're going to do in this lesson is basically three things. First, students will recognize and use interval notation for domain and range. Students will differentiate between bounded and unbounded intervals. And students will find the domain and range from an equation. What you should already know is that using function notation means that we use f of x instead of y in an equation, and we'll review that a little bit in a couple minutes. Our essential question today is how do we find the domain and range of relations and functions graphically and algebraically? And what you will be able to do at the conclusion of the lesson is to find the domain of the function, such as this one shown on your screen in the bottom right. All right, I'm going to pause right now so that I can switch to the notes. Here is our 1.2 notes on functions. So remember, you should either have this printed out and start to fill it in now, or you can fill this in on your own lined paper. For the definitions at the top, feel free to abbreviate or shorten if you're writing this on your own paper. But here's the important definitions that we need for today. First of all, functions. From set A to set B, a function assigns each element x, the x values from set A, to exactly one element y in set B. And calling these things sets might be a little different, and we'll see some examples of that in example 1. But basically we have like a set of x values and a set of y values, and the x values map to the y values. The x values are also known as the domain or the input, and the y values are also known as the range or the output. And these definitions right here may be new. So there's different ways that you might have learned domain or range in the past, but for today, what we're going to talk about is a domain is a set of values, and they cannot repeat and all must be used if something's being called a function. And a range, the values may repeat and not all must be used. And we'll see, again, examples of that. Function notation, as we mentioned, uses f of x instead of y. And then we have interval notation. Interval notation looks something like this. If you might have a bracket or a parenthesis on either side, and inside you have two numbers with a comma. So bracket 3, comma 8 parenthesis is the interval of real numbers between 3 and 8, including the 3 and approaching but not including the 8. We use a capital U symbol to connect two intervals, and we always use parentheses if we have an infinity as an endpoint. All right, we'll come back to interval notation, but let's take a look at example 1. Given these two sets, set A and set B, we want to know which sets of ordered pairs represent functions from A to B. And we're going to use our very specific definitions up here that you see in the parentheses. So first off, in letter A, we have sets of ordered pairs as our relations. All of these are relations. We're trying to determine if they're functions. So we're going to look first at the first values. You can think of these if we're plotting them. We have 7, 9, 9, and 8 as our x values. Those do come from set A, and we want to know if it's from A to B. But one of our definitions of domain says that the values can't repeat. So because the 9s repeat here, this is not a function. For letter B, we have 3 x's this time, 7, 8, and 9. We've used all 3 values from set A. They did not repeat, and they were all used, so that part's good. And then for part B, set B rather, the range, the values are allowed to repeat, not all must be used, but we have a 1, a 2, and a 3. Those all do come from B, so this is a function. And it does go from A to B. It maps every element of A to an element of B. If we look at letter C, we do have a function here. Technically, none of the x values repeat, but this is not from A to B, right? We don't map elements from A to elements of B. So this is a function, but it's not mapping from A to B. And letter D, we have 7, 8, and 9. So we have every element from set A once, and all of the y values come from set B. They're allowed to repeat. They don't all need to be used. So this one does work. So that, again, is a very specific definition of domain and range in reference to sets. We won't often see it like that. Most of the time you'll see a graph or you'll see an equation, but I figure we should throw this in here since technically this is a type of domain and range. Let's take a look at example 2. Now we're going to determine whether equations are functions. Which of the following equations represents y as a function of x? We're going to use the vertical line test to help us out here. So the easiest way to graph an equation is to solve for y equals first. So in this first one, we're going to subtract x squared. We end up with y equals negative x squared plus 1. And this hint over here is going to be key. We're going to use the vertical line test. So I'm going to pull my calculator up here. I'm going to go to y equals, and then we're going to type this in and see what it looks like. Negative x squared plus 1. Graph. All right, I've got a little bit of a weird window here, so I'm going to press zoom 6 to reset it. And you can see this is a quadratic facing down. If you don't remember that term, we'll get to that in a lesson or two. Negative x squared plus 1. So the vertical line test, you may remember, says that if you hold a pencil or any sort of vertical line and kind of brush across your graph, it should only touch at most one point of your curve or your line at a time. And this does pass that vertical line test. So this is a function. Okay, and then for letter B here, again, we're going to solve for y. This one gets a little weird because we have to do a square root. And something important to remember is if you initiate a square root, you have to put a plus or minus in front of it. Because technically, you could take a positive number squared or a negative number squared and get the same answer. So plus or minus is necessary here. So in order to graph this one, I don't want the light to be reflecting on the screen, so I'll put it over here. I'm going to have to actually do this twice. So we're going to do square root of x plus 1 and the negative square root of x plus 1 to account for the positive and the negative version. Take a look at the graph, and you should be able to see, once it finishes, that even though this is two different colors, it's representing the same equation, and it does not pass the vertical line test. Anywhere over here, it's touching 2 points at the same time. So this is not a function. Hopefully you remember that from previous years. That takes us to an intro to function notation. If g of x equals negative x squared plus 4x plus 1, we want to find the following. So for g of 2, and it's important to know, right? This may be common sense for some of you, but g of 2 does not mean g times 2. G of x doesn't mean g times x, even though that notation also means multiply in another context. This is actually talking about g of x, or g of 2. So g of 2 is just another way of saying y equals. But this means that we need to plug in 2 for every x. So it's going to be negative 2 squared plus 4 times 2 plus 1. And if we multiply that out, 2 squared is 4, so we get negative 4 plus 8 plus 1, and we get 5. For g of t, that simply just means replacing every x with a t. So we get negative t squared plus 4t plus 1. And that's all we can do there. And for the third one here, g of x plus 2, now we're replacing every x with x plus 2, which is kind of weird, but we can do it. So negative x plus 2 squared plus 4 times x plus 2 plus 1. And I think we should simplify this. So I'm going to multiply out the x plus 2. So I get x plus 2 times x plus 2, which becomes, if I FOIL, x squared plus 4x plus 4. If you need to see that, it's x plus 2, x plus 2. And we have to do first, outer, inner, last, like that. And we end up with x squared plus 2x plus 2x, which is 4x, and then plus 4. Okay, so we did the squared. We can distribute the 4 here. We get 4x plus 8, and then plus an extra 1 on the end. Next, I'm going to distribute this negative. So we get negative x squared minus 4x minus 4 plus 4x plus 8 plus 1. And then we're going to combine like terms. So the negative 4x and the positive 4x actually are able to cancel out. We only have one x squared term, so it's negative x squared. Negative 4 plus 8 plus 1 is going to give us a plus 5. Great. So there are the examples for, or there are the answers for example 3. Okay, we have one more side of the page to go, so let's flip this over here. In example 4, we're going to find all real values of x such that f of x equals 0. So this is a little bit more of a practice with function notation. So in letter A here, we are actually changing the whole f of x to 0. We're not changing x, so it'll be like this. And then we're going to just solve for x. So we can subtract 10 to the other side. And then divide by negative 2. And we get x equals 5. Great, that works. And in letter B then, we're going to change the f of x to 0 again. All right, and this is where we get to factoring, because there's no way we can straight up solve this for x like we did in letter A. We actually have to factor the quadratic like this. And this sometimes causes students some trouble because it's been a while potentially since you've seen this, especially if you took geometry last year. You might not have factored in over a year, but x squared is definitely going to break down into x times x. And then what we need to do is we need to find two numbers to put here and here that multiply to get 6 and add to get negative 5. And that's going to be a negative 2 and a negative 3. So if you think about foiling this, you would get x squared minus 3x minus 2x, which gives us the minus 5x. And then the last terms are negative 2 times negative 3, which gives us the plus 6. If you need more examples of that, or you need more help with that, please let me know. Especially if we can meet in person, then we'll be able to do that. So then we set each factor equal to 0. And for this first one, we're going to get x equals 2. For the second one, we're going to get x equals 3, because it's x minus 3 equals 0, which I could write that in. Add 3 to get x equals 3. Same here, you get x minus 2 equals 0. Add 2 to get x equals 2. All right, so there's our two solutions. This one actually had two solutions. And then we get to C and D. So for C and D, we're going to find all the values of x for which f of x equals g of x. So we're just going to set the left, or the f of x, equal to the g of x, and then solve for x. So we have x squared plus 1 equals 3x minus x squared. And then I'm just going to start to solve this for x. So the first thing I'm going to do is add x squared to the other side. And we get 2x squared plus 1 equals 3x. And it's becoming pretty clear to me that the x's and the x squareds are not going to cancel out. So I'm going to have to solve this like a quadratic. So I'm going to subtract the 3x to the other side. There's no term, like term for it to subtract from. So we're going to get 2x squared minus 3x plus 1 equals 0. And we have to factor. The correct factoring here is going to be 2x minus 1 times x minus 1. And you're going to need to be able to do that on your own, so make sure you can do that. So we get 2x minus 1 equals 0 and x minus 1 equals 0. And then once I solve each of these for x, I'm going to get x equals 1/2 and x equals 1. Okay, and then for letter D, we're going to do the same thing. We're going to set the f of x equal to the g of x and then solve. And I'm going to add x squared to both sides. So I'll get 2x squared minus 1 equals x plus 2. Then I am going to subtract the x and subtract the 2. So if I subtract x, I'm going to get a negative x. Subtract the 2, I'm going to end up with negative 3. So I get 2x squared minus x minus 3 equals 0. Again, we're going to need to factor this. It'll be a 2x and an x. And now I need to figure out how do I multiply two numbers to get negative 3. But once I combine them in FOIL, I get negative x in the middle. It's going to end up being 2x minus 3 and x plus 1. And then we set each factor equal to 0. Solve for x, and we're going to get x equals 3 halves and x equals negative 1. All right, there we go. One more example, example 5. Some more practice with domain. So here we go. In letter A, we're finding the domain of a set of ordered pairs. And remember, domain means the x values or the input. So when you're actually given a set of ordered pairs, how you would write that? Usually I put a D and a colon to represent domain. So if it's just going to be a list of x values, I usually put it in brackets, and I want it to be in numerical order. So it's going to be the negative 3, the negative 1, the 0, the 2, and then the 4. So that's the whole domain for that one. If any number is repeated, it wouldn't be a function, but it still technically could have a domain if it was just a relation. You just don't need to write the same number again. You only need to write it once. All right, and letter B. Now we have just a whole equation, and we want to know what's the domain of this equation. So to figure this out, we got to think about what the graph looks like. And you know what? Might as well graph it. So if we take a look at our graphing calculator here, if I enter 1 over x plus 5 and graph, looks like this. Now, my graphing calculator here just isn't super precise. So this curve actually keeps going this way, and this curve keeps going this way. There is kind of a vertical asymptote going on right here. Asymptote meaning that the curve approaches it but never touches it. And we can figure out where that is because remember that a denominator can never equal 0. So to figure this out, we have to take a look at the denominator and figure out when does it equal 5. When does the whole denominator equal 0? And if we subtract 5, we get x is negative 5. So the domain is everywhere except negative 5. And how we would write that is in interval notation. We're going to write that it can go from negative infinity up to negative 5, but not touching it. So we use the parenthesis. And then a U for the union. And then we go from negative 5 to infinity. All right. So it might have been a while since you used interval notation like that. And I want to look at the graph too, so you can see this. Take a look. The curve, domain is all the x values. So we're going to focus on the x-axis here. We're going from negative infinity to negative 5, and then we have to have a break because at negative 5, there's no y value. So we go from negative infinity to negative 5, parenthesis, not including the negative 5. The union, it picks right up right on the other side of the negative 5, and then goes all the way to infinity. So we look along the x-axis from left to right, and then we have to write down all of the endpoints of the intervals. We're going to see a couple more examples of that. Let's take a look at letter C. All right, so for letter C, we have a function, square root of 4 minus 3x. There is a rule that you cannot take the square root of a negative number. That would be an imaginary number, and we're not getting into that right now. So what we do need to know is where is the endpoint of this square root? Where does it stop existing? And so to figure that out, we're going to take the inside and set it equal to 0, because when it changes from positive to negative, or when it crosses 0, that's when we're going to start to have an issue. So if I solve this for x, I'm going to subtract 4, and then divide by negative 3, we get x equals 4/3. And I'm going to look at the graph just to verify this. So if we take a look at the square root of 4 minus 3x, you can see the curve stops. And again, this calculator isn't precise. It actually touches the x-axis right here. It's just too zoomed out, so you can't, the pixels aren't willing it to show us that. But it stops right at 4/3. And so it's going to be from negative infinity to 4/3, and then it stops. Now, does it exist at 4/3? You can take the square root of 0, right? If I plug 4/3 in for x, I get 3 times 4/3 is 4, so 4 minus 4. Square root of 0 is 0. So I'm allowed to do that. So for the domain for this one, again, based off the graph, we saw that we could go from negative infinity, and then we stop at 4/3, including the 4/3, because 4/3 does exist. It gives us a y value of 0. So it works. But it does not pick up again. That's the end. All right, for letter D, this one's kind of a trick question. This might look familiar to you. This is a volume formula. 4/3 pi r cubed is the volume of a sphere. And so we got to think about this. Can there be a limit to the r's that we can plug in here? And there's no limit based off of the equation itself. But if you think about it, volume must be positive. So the radius that we can plug in also has to be positive. And so the only limit to the domain is that it has to be positive and not 0. So it's going to be from 0 to infinity, not including the 0. Again, that was a little bit of a trick question. That's just because for volume, it can't be negative. And this last one, f of x equals the square root of 4 minus x squared. We're going to treat this the same way as we treated letter C. We're going to try to take the inside and set it equal to 0 and see if we can solve this for x. So I'm going to subtract 4 and then divide by -1, and we get x squared equals 4. I'm going to initiate a square root, which means I have to include the plus or minus, and the square root of 4 is 2. So it's going to be plus or minus 2. All right, so we got 2 answers, 2 and -2. We only got 1 answer over here. Let's take a look at what this graph looks like. It's the square root of 4 minus x squared. And it's very weird. It's a semicircle that goes from -2 to 2. So the x values, if I'm looking from left to right along the x-axis, are going to be from -2 to 2. And I plug in 2. 4 minus 2 squared gives us the square root of 0. So it does work. Same thing happens for -2. We plug in -2, we get 4 minus 4. And that's still 0. Square root of 0 is 0. It exists. So that's going to be our domain there. Now, a lot of the questions on the worksheet associated with this lesson are based off of graphs. So you are going to need to make sure that you can look at a graph like this and be able to tell across the x-axis for the domain and up and down across the y-axis for the range. So you get some good practice with that in. That's the end of the notes. So thank you very much for watching, and best of luck with the additional assignments. Thank you.